Hi, and welcome to Module 2 of Lecture 15. In this module, we're going to use some examples of what we did in the previous module. So remember in the previous module, we introduced the concepts of optimization in more than one dimension, and then we focused in on one particular kind of optimization, unconstrained optimization. I call it unconstrained optimization, with optimization in which there are no constraints in the possible values of the variables we're optimizing over. So there's no bounds on the values they can take, there's no budget constraints or anything else, it's just unconstrained completely. Now, these problems in general don't only have two variables, but it's fairly difficult on a relatively small tablet to write up ones with three variables because you have three equations and three unknowns, you have 3x3 Hessians, and it gets real messy and hard to write on a single screen. There's a 3x3 example, a three variable example in the text, and you can go through some more examples of that in the problem sets if you care to. And there's some more examples of that in the textbook as well, and exercises. But here we're going to cover two-dimensional examples, so functions of two variables. That said, all the same logic applies. There's nothing different conceptually, it's just more algebra to deal with three variables. And given that we've already done the component algebra pieces in previous lectures, so we've solved three equations and three unknowns in previous lectures for linear equations. We've calculated determinants of 3x3 matrices. We've calculated the eigenvalues of 3x3 matrices. So we've done all the component pieces already. This is, so using two variables doesn't really lose us anything. It just allows us to make a neater example. Okay. So I listed three examples on here. I'm going to go through each one of those. The first example up here is the only one that has some substantive attachment. The other ones are just made up. And that first one corresponds to an individual trying to make a policy choice in two dimensions, where that individual has an ideal point of z, the vector z. So you have some two-dimensional space. Maybe one dimension is guns, the other one's butter. Maybe one's social policy and one's economic policy, whatever. It's two-dimensional policy space, and you're trying to pick a policy x that maximizes your utility given your ideal point of z. Now, this is not a terribly interesting problem. You might guess when you use the word ideal point that the answer is pretty clear already, and it will be, as we'll see in a second. But it serves as a good example because it deals with completely separable variables. X does not multiply y ever. Sorry, x1 does not multiply x2 ever, so it's relatively straightforward to compute. So it'd be a good first example. Okay. So we're just going to go through all the steps that we talked about in the previous module and evaluate them with this function. Okay. So step one. Step one was calculate the gradient of f. Okay. Well, here there are two components to the gradient. Remember, the first component is the first derivative, is the derivative with respect to x1, the partial. The second is x2 partial. Now, if you remember back to calculus, the change of variable formula, because x1 minus z1, the derivative of that with respect to x1 is just 1, we can pretty easily change variables to u equals x1 minus z1. U prime here is just 1. Du dx is just 1. So nothing to multiply, and the derivative of negative u squared is just negative 2u. So the derivative here in the upshot is just going to be negative 2u, which is negative 2x1 minus z1. If that was way too fast for you, I highly advise you to stop right here, go back to the stuff in calculus, and try to revisit that to get more practice. As I said at the beginning of these last few lectures, they definitely require a firm understanding of all the previous stuff we've done, particularly the stuff in calculus and linear algebra. So if you don't have that firm understanding, stop here, don't continue on, go back to that, look at it again, try to improve your understanding of that stuff because it's necessary background for this stuff. Okay, so that's the first one. The second one is the exact same thing with the 2, so it's right over here. And now we have the gradient of f. First step done. Okay. Second step, compute the critical points. So the critical value is x star, then make this thing equal to 0. Well, that gives you here two equations and two unknowns. That's the zero vector. The first equation is negative 2x1 minus z1 equals 0. That's the first component. The second one is the second component. Good news here is there's no x2 in the first component and no x1 in the second equation, rather. Therefore, solutions don't require solving simultaneous equations. You can solve each one separately and get x1 equals z1. So this would be stars. These are the critical values. and x2 star equals z2. So not surprisingly, the only critical value, the unique critical value, sets x vector equal to z vector. Why not? You have an unconstrained problem. You can choose whatever policy you want. Why not choose your ideal point? You probably guessed that immediately. And there you go. The math showed you right. That's step 2. But still, we're going to finish off to get an idea of what's happening. Step 3, the Hessian. Now the Hessian, recall, and I'm not going to do this every time, just this first example. The Hessian is partial squared f dx1 squared. The other diagonal term is partial squared f dx2 squared. And on the diagonal, off diagonal terms is the cross partial derivative. And that's the same up here as well. I'm sorry for being too small. I'm trying to fit this into one screen so I don't have to make you flip back and forth in the video. Okay, again, why we use 2 variable examples. There's the Hessian. Well, the off diagonal terms are 0 because this is the gradient, right? It does not depend on x2 at all. Therefore, when you take the derivative with respect to x2, this is treated as a constant, and you get 0. So the off diagonal terms are 0. What about the on diagonal terms? Well, each one's the same. Differentiating this again with respect to x1 just gives you -2. Same thing with the bottom one. And here's my Hessian. That's step 2. To do step 4, we want to know if it's positive or negative semi-definite. Well, we can positive, negative, definite. We can just look at this. Well, -2 and -2. We can find our eigenvalues. Okay, that's the eigenvalue equation. We get lambda plus 2 squared equals 0 is the eigenvalue equation. That implies lambda equals -2 and -2. There are 2 eigenvalues, they're both the same, they're both -2. All eigenvalues are negative. That means it's negative definite. If the Hessian is negative definite, we know that the critical point is a local maximum. Since it's the only one, we don't do step 5 at all, so to compare, it's a local maximum, it's the only one, so it's also a global maximum, and we're done. That tells us that we found one global maximum, x equals to z, and that's the global maximum, and that's it. That's all there is to this. Just going through the steps, which are exactly the same steps we did back in part 2 of the class, but optimized in 1 dimension. So the first example. Let's do the second one, which will be a little more complex. Okay. Second one. That's right here. So I'm going to do this one in, I don't know, blue just because. So there you go. Second one. Same steps. So first step, compute derivative, compute gradient. Because we never need to put them in a vector anyway, I'm just going to save some space and do each one separately. So this one, 2x from the first term. Second term is -y because it's a constant. Third term is 0 because y squared is the constant with respect to x, so it's a 0. Third term is -2, and fourth term is 0. There's the first one. Second one is going to be, first term is 0, second term is -x, third term is +2y, fourth term is 0, and fifth term is +10. Okay, step 1. Step 2, set the gradient equal to 0, the 0 vector, which means setting each one of the components separately equal to 0. So the first one is going to be 2x minus y minus 2 equals 0. And the second one is -x plus 2y plus 10 equals 0. Well, let's solve this quickly. They're all linear, so it should be relatively straightforward. But they are linked, so we have to do simultaneous equations. The second one, and these are all critical values here, but I'm going to drop the stars to make it more readable. But there should be asterisks on all these x's and y's in this part 2. So x is going to be equal to 2y plus 10. That implies we can plug it in over here to get 2 times 2x plus, 2y plus 10 minus y, minus 2 equals 0, which implies 4y minus 3 minus y is 3y. 20 minus 2 is 18, so it's 3y plus 18 equals 0, or y equals negative 6. And they can plug a negative 6 over here, which implies x equals negative 12 plus 10 is negative 2. I'll put the stars back on there. So the critical values are, the critical vector here, a star, x vector, is equal to negative 2 and negative 6. There you go. So step 2. Step 3. What's the Hessian? Well, here's the first derivative. Taking the partial again with x, with respect to x gives you 2. With respect to y gives you negative 1, that's the cross partial. Now go to the second equation for the second row. The cross partial is negative 1, as it should be, because it must be symmetric. The Hessian must be symmetric. And here it's symmetric in y too, y as well, so we have a 2 as well from this one. Taking the partial with respect to y of the second equation gives you 2. Here's my Hessian. Step 4, what's the eigenvalues? Well, it's going to be the Hessian minus lambda I. So determinant of 2 minus lambda, minus 1 minus 1. That equals 2 minus lambda squared, 2 minus 1, that's equal to 0. That implies you have 4 minus 4 lambda plus lambda squared minus 1 equals lambda squared minus 4 lambda plus 3 equals 0, or lambda minus 1 times lambda minus 3 equals 0. It factors nicely, and lo and behold, you get lambda equal to 1 or 3. There are 2 eigenvalues, both are strictly positive. Therefore, this is positive definite Hessian. Hessian that is positive definite has the critical point. The critical point of the Hessian that's positive definite is a local minima. Right here, the Hessian's positive definite, so the whole thing is globally convex, and you have a local minima at 1, 3. Sorry, at negative 2, negative 6. Step 5, there's no other things to compare it to, so we have a single critical point here, and this is a global minimum. That's it. Then step 2. Then example number 2. Okay, we'll do one more example that's a little more complicated, that has more than one possible solution. We'll do it again. And we will, let's do that in green to be different. Okay, so now we're over here, the last one. Again, still 2 variables though, so the first step is computing the gradient. We're going to have the gradient of the first one. What am I doing? Oh yeah, sorry. So x of f is going to equal 3x squared using the power rule, plus y squared, since y squared is a constant, minus 2y squared x, since y squared is a constant. And the second one's going to be dy, partial y. We get the first one's a 0 because there's no y there, plus 2xy because x is a constant, and minus 2x squared y, since again x squared is a constant. Step 2, set equal to 0. Well, that gives us 2 equations. They're not linear equations. And 2xy minus 2x squared y equals 0. Now, there are squares in here a whole bunch, so it's not going to be a nice easy linear equation. However, what we can do is use the second equation here to try to help us figure out more quickly what the answers possibly are. Okay, well, first note, there's an x in both terms. So if x is equal to 0, that equation is solved. So one possible solution from this equation is x equals 0. Similarly, if y equals 0, since y is in both terms, then the equation also equals 0. So y could equal 0. If neither x nor y equals 0, you can divide through by x and xy, and you end up with 2 minus 2x equals 0, or x equal 1. So we have three possible ways of solving the second one. Either x is 0, y is 0, or x equals 1. So those are solutions. We can now go to the first equation again. If x equals 0, then, so let's do the a, b, and c. So this is a, this is b, and this is c. I'm going to do this up here. So if x equals 0, the first equation implies y squared equals 0, or y equals 0. If b, then the first equation implies 3x squared equals 0, or x equals 0. So if either x or y equals 0, then the other one also equals 0, and you get one single possibility, 0, 0. So we have one critical point, possibility of 0, 0. And this is 1. Now if c, we have x equal 1, then we have 3 plus y squared minus 2y squared equals 0, or y squared equals 3, or y equals the square root of 3, so plus or minus square root of 3. Okay, so now we have another two possibilities. Or, try from going in one direction here. We have 1 square root of 3, that's number 2. Or we have 1 negative square root of 3. That's 2. Okay. So we have 3, and this is number 3 rather, not 2. So we have 3 possible, and I'm sorry, this is for the negative square root of 3 up here. We have 3 possible solutions to check, okay, which we might expect given the situation here. Let's check them. First thing first with 0, 0. Okay, so first we're going to calculate the Hessian. What's the Hessian? Well, the first upper left one is going to be the derivative of this one, the first one up here, the first equation, the first derivative rather, the partial with respect to x is what I'm trying to say. So the first term is negative 6x minus negative 2y squared. I really should have left more room. Let's just forget this thing over here. Can't erase, unfortunately. The cross partial is the derivative of this with respect to y, which is y is 2y minus 4yx. Okay. Now we go down here. Now we're taking derivative of the second equation here. The partial with respect to y. With respect to x now, we get, as we must, 2y minus 4xy again. It's got to be symmetric. And now we do with respect to y, we get 2x minus 2x squared. Sorry about the thing in the middle there. This is your Hessian in general. Now, we have to evaluate this at each one of the possible critical points, and there are 3 of them. So, at 1, if x is 0 and y is 0, everything's 0, so the Hessian is just a 0 matrix. Okay. At 2, the Hessian is evaluated at 1 square root of 3. Okay. So at 1 here you have negative 6 minus 2 times the square root of 3 squared. Square root of 3 squared is 3. 2 times 3 is 6, so it's negative 6. So it's negative 6 minus 6. That is negative 12. The second one is going to be 2 times the square root of 3 minus negative 4 times the square root of 3. That's negative 2 square root of 3. Not enough room here. Same as the one over here. Negative 2 root 3. And down here you have 2x minus 2x squared would be 0. So 2 minus 2 is 0. There's that. And the third one is the same thing with a minus the square root of 3. That changes nothing in the upper left because it's squared, so it's still negative 12. And let's see, and the lower right, same thing, it's still 0. Now we have the flip sign though on the diagonal, so we have 2 times the square root of 3 and 2 times the square root of 3 instead of negative. And there we go. So we have 3 options. Now it's going to be messy, but note first, in the first case, if the whole hash is 0, the eigenvalues are 0, the determinant is 0. So in the first case, so this is step 4 now, in the first case, the determinant is 0, and we have an indeterminate critical point. So we're going to forget that for now. That's an indeterminate critical point. Second case, what are the eigenvalues? Okay, let's work on that. We have determinant of h minus lambda I. That's going to equal negative 12 minus lambda. That's negative lambda. And negative 2 radical 3, negative 2 radical 3. Note that actually, because these two things will multiply, the off-diagonal terms will multiply, whether or not they're positive or negative is irrelevant. So this is actually the same for step 3. It's the same exact eigenvalue as step 3, so we just do this once, luckily. Which is a good creep. I had room in this paper on the screen. So what's this? Well, it's negative 12 lambda, sorry, positive 12 lambda plus lambda squared minus 4 times 3 is 12 equals 0. You have, that implies lambda squared plus 12 lambda minus 12 equals 0. I don't know this offhand, and I think I'm running out of room here, which is very unfortunate. But let's do the quadratic formula for this thing. And what do we get? We get, what is this 2? I apologize, these should be 4s. Up here, made a mistake, sorry. These are 4s. So these are 4s. And we get 2 from there. Oh no, those are 2s. Sorry, double mistake. These are 2s. Everything was fine before. Ignore what I just did right there. They were 2s. So now we have this. What's this? How do we solve this? We solve this using the quadratic formula. So that's lambda equals negative 12 plus or minus negative 12 divided by 2 plus or minus 1/2 times the square root of 144 minus 4ac. That's plus 48. So we have negative 6 plus or minus, let's see, the square root, 1/2 the square root of 192. 192 divided by 2 is 96. 96 divided by 2 is 48. So this equals negative 6 plus or minus square root of 48. Square root of 48 is slightly less than 7, because square root of 49 is 7. So one of these is positive and one is negative. Because of that, you have neither all positive nor all negative, so this is a saddle point. So after all that messy algebra, what we end up with is our three critical point possibilities. One's indeterminate, the other two are saddle points. Go us. But the major point of this, and hopefully you can follow that on the screen again, this is about the limit of what this tablet can handle, and I don't want to flip screens because then you lose all the previous math in the video. Unlike, on paper you can just flip back and forth on paper. On a video you can't really do that, so I want it all on the same screens. When you pause and sit there and stare at it, it's all there for you. But it might be a little messy and I apologize for that. Anyway, that's it. You've seen now several examples of multidimensional optimization. I hope, despite the more complicated algebra, that you have seen that it's really just the same conceptual material that we did back in part 2 of the class, when we had, first we find the first derivative, here we find the gradient, then we find the critical points. We do the same thing by setting the gradient equal to 0, or the first derivative equals 0. Then we take a second derivative, or the Hessian, evaluate at the critical points. Then we see if the second derivative is positive or negative, or positive definite or negative definite. I apologize. I think I've been saying positive semi-definite early on. You want positive definite for local minimum and negative definite for local maximum, not semi-definite. I apologize for the confusion there. Okay, and that's it for this. In the next two modules, we're going to introduce and do fewer examples of constrained optimization with inequality constraint. Thank you very much.